Okay, since time is up, we are going to start the presentation. Can you see the screen now? Thank you. Hello. So, okay, let me start. My name is Hyeongu Kang from the EQS-SQRT, and today I would like to present about the paper name Hamiltonian simulation by Qubitization. So, I will just briefly talk about the overview. So I will just like this paper like wants to prove some theorem, and I will just briefly tell what is this theorem is, and then give some kind of background things, just one or couple of things, and then go through like what is the qubitization and the quantum signal processor that this paper is talking about, and then how did the authors like design the operator function, and lastly how these are related to the Hamiltonian simulation. So this is a paper from the 2019 quantum, and there's some consecutive works related to the slide. So if you want to see more things, then you can maybe refer to those things. So since there's some kind of there's some freshmen on sophomore, I will just briefly talk about the Hamiltonian simulation. So if we have a Hamiltonian H, and if we want to simulate it, we should like construct the time evolution operator e to the minus IHT, this one. But however, this Hamiltonian have some various terms. And for the very simple case, it may have like two terms. But if we have those two terms, because they are not generally commutating, they cannot be decomposed into like these forms. They are composed like these forms, and it is kind of a problem. And so it is kind of a very annoying thing. Yeah, this is kind of very introduced. And the statement that we want to prove now is that if the Hamiltonian, the Hamiltonian, it can be expressed in this form for the sum unitary and for the sum seat preparation unitary. So A is for the ancilla qubits. Then we can simulate this with the Crowley complexity with t plus log 1 over epsilon. So t is the time that for the Hamiltonian's evolution, and epsilon is for the errors. So this is the statement. There's some kind of long things, and I will just go over this in the next. Go over this again. So this is the comparison with the previous works, and this was the state of art in the 2019. I remember that this did not change a lot, and as you can see, like core complexity is not that different from the previous things in this work, but the ancilla qubits are very good if you consider the scaling. And now just a brief just introduction or the thing about the Chebyshev polynomial. It is just the expression of the cosine and zeta in terms of the cosine zeta. And why I'm telling this is like we use this in the later. So we can like easily get the recurrence relation. And also it is orthogonality. So it is just the best polynomial basis for the L infinity function approximation on a finite interval. So you can go for this reference for the further details. So let us begin. So this is about the definition of the standard form. I will just tell a little bit more in the next slides. But for just a signal operator H hat with a spectral norm that is at most one, it can be like encoded in the larger Hilbert space. So we have a kind of a unitary oracle that can embed this one. So I will just show like how can we express the H in standard form. Like everyone, if there's some like a Hamiltonian, we can like do like UJ or like T or swap or unitary. So there's some various cases, and it is just a table that showing that it is possible for some various cases. And note that we want to express Hamiltonian, and the things that we want to construct is the function of the Hamiltonian. So these are the few examples, and these are not that important, so I'll just briefly skip it. So if there's, in the case of the Hamiltonian expressed as a linear combination of the unitaries, we can get the state preparation oracle this one, and unitary operator this. And the proof is just a straightforward thing, so I'll just skip it. And this is same for the purified density matrix. So just a calculation, so I'll just skip this for now. And now we begin our talk about the qubitization in a quantum signal processor. So I'll just explain about like what is the quantum signal processor, and then what is the qubitization, the core theme of this article. And the first one, like we have some kind of signal operator H, and as I told before, the signal oracle U embeds this in a larger Hilbert space. So we can like define U and G like in these terms. So if we measure it correctly, then we get HG, this one, and the probability is this one, as you can see. So naturally, this is kind of probability, so it cannot exceed 1. So it gives some kind of confinement for this. Also, let's consider the case when H is a Hermitian matrix. There's an argument on the paper about the normal matrix too, but it is a very lengthy thing, and I don't have enough time for that, so I'll just skip it. So if you have further interest in the case of the normal matrix, please see the appendix of the article. And we can just like decompose this in like these scales. And our goal is to find the optimal quantum circuit that transforms the standard form H written in the standard form, into the FH. So all we want to do is like, if H is given the standard form, we want to find FH. And the further contents talk about like, does this always possible, or like how can we explicitly like construct these things? So this is the definition. There's some bunch of things, but the core thing is that we have a Hermitian function and a Hermitian matrix and a function. Then we can like give a standard form encoding of the FH. And the sources that we use is like encoding of H and a constant number of like additional qubits. Like you can see in the like we use for like answer qubit or else, and arbitrary few gates and some constant numbers of additional gates. And note that if we apply this unitary like multiple times, one may expect to get a like squares of H. For example, like we repeat this process and someone wants to like get a H square, because like do 3 times and we get a H squared. Some would expect those things, but this is not generally true, because like U is not invariant under the eigenvectors of the H. So that's the kind of problem. And to resolve this problem, we introduced the iterate. So this iterate is the thing that this acts like somewhat U, but for the each eigenstate of the H, it just perform a rotation in SU2. So we can, in the H lambda space, we can just define some like Pauli matrices too, because it is just a 2-dimensional space. Yes, and we will just talk about a little bit more about this later. And on a general input, we can express this in this, like lambda represents the H lambda space, and so it is just like a rotation here. So, and where the zeta lambda is defined through this equality, Now we talk about the qubitization. So if the Hermitian matrix H is encoded in a standard form, as described in the like this definition. Oh, sorry. The iterate we define, this one, can be constructed using at most 1 Curie to like G hat and control U and other things in a quantum gate. This I will just give this one, and like note that like doubly and efficiently reproduces the Chebyshev polynomials. That's because like recall that the Chebyshev polynomial, like the Tn cosine theta is cosine n theta, and this is kind of rotation. So we repeat this like n times. It gives something like the n theta rotation, and it is kind of related to the Chebyshev polynomial. So we can like effectively make this polynomial. And these are the basis of the polynomials polynomial space. So we can like approximate the FH, which is written like AH plus IBH. So these are the two kind of big theorem in our presentation. So first one is like the ancillary quantum signal processing, and it means that if the real polynomials have some certain conditions and we have some iterate, we can like get a standard form encoding of AH plus IBH. And this stands when A and B have some equal parity. And for the case of when these two have an opposite parity, there are some different conditions, but we can also get AH plus ICH kind of thing. The only difference is just the number of the ancillary qubits. There's a proof in the back part. So for the qubitization, like we assume the G is known. In fact, we don't have to know it exactly. Like we only have to know some query about it. So all we need to do is like we want to find some S that S prime that acts on an ancillary register, and that transforms U into the iterate W. And we can like calculate, find this one as the following calculations. And there's some conditions on qubitizations, like for all signal oracles, like that implement expresses H hat in the standard form, that creates a unitary iterate with the same signal operator in the same basis, but in SU2 invariant subspace containing G if and only if we can find such things. So I would just skip this proof. And this gives the reflection, qubitization of reflection. It is kind of a complicated, sophisticated thing. So if you just like keep the feelings of it, just so for all signal operators, like if it satisfies those things, then we can like implement the Hamiltonian operator, and the unitary iterate this one implements the same signal operator. And now we talk about the existence of the qubitization. Like for all the signal unitaries that implement the Hamiltonian signal operator, there exists some quantum circuit U prime using at most one more qubit that controls this. The chorus controlled U hat and U hat dagger wants to implement the same signal operator. We show this by the direct construction. So we have like these two controlled U operators. Like first one, just a controlled U dagger. This one is a controlled U, but the control qubit is kind of opposite manner, in an opposite manner. So if we multiply these two, we get this. And if we like use this ancillary state as this and define this, this will satisfy the conditions. This is just a calculation, so I will just skip this. And now we will use these facts to prove the ancillary quantum signal processing. Before diving into this, I will just define the phase iterate. So we defined the iterate, but we now consider the like phase iterate. So it is kind of a iterate that parameterized by the phi, and where phi can be defined like this. And we have some useful thing. We can like express this in the sense of the W hat with the Z hat. This is the Pauli matrix defined in the lambda self space. This is the proof, and as you can see, it is just also again a direct calculation that just demonstrating that it just holds. The lambda again means the lambda subspace. And now this is the theorem that we want to prove. Remember the equal parity. So we can express the Q phase iterate as the follows. So it is just something very similar to the like unitary, this one, the single qubit rotations. So similar to this manner, we can like express these into like linear combinations. The combinations of like the Pauli matrix and the lambda subspace, and this gives not that intuitive like relation with these two, but we can like figure out that the choice of phases can control this. This whole thing is like in each subspace, this is a product of SU2 rotations. So if we consider the single qubit rotations, it is just written like this, and this can be characterized well. The further details in the in the references. And now we want if we want to prove this lemma. So this is kind of a really lengthy thing, but it is directly related to this theorem. See the similarity between the conditions. A1 equals 1 and a square plus b square is smaller than 1, and it has similar things. So it is just a direct correspondence. So the unitary operators in the H subspace, H lambda of like this W psi are isomorphic to the like product of single qubit rotations, as you see here. This one. And we identify zeta lambda as this, and we can recall that zeta lambda is defined as this one. This one. So results from the lemma 3.3, we can like get the direct answer by this one. This is from the reference, and it is kind of a lengthy thing, and I cannot cover all the parts, so I will just refer to the reference. And now we talk about the single ancilla quantum signal processing. This one is proved in a very similar manner to the previous thing, but it is a little bit more complex. So given a unitary with eigenstates that has like amplitude 1, we can like think about this controlled unitary. And if we consider the following sequences, this is kind of a tough thing, but the only thing matter is the result here. So we can again express this in the terms of like this ones. So again, the Pauli matrices and the lambda subspace. And then note that this is similar to the ancilla free case, but it only acts on the ancilla. This one. Compare this with this one. So this one acts on the different space. And now we bring this theorem from the reference. So A theta is kind of a real cosine Fourier series, and C theta is a real sine Fourier series, and A0 is 1, and A squared plus C squared is at most 1. Then we can find some psi that can be computed in this polynomial time. But in reality, we cannot like get the like exact A and C. We might given like A and C, they're real close to those kind of A and C, not exactly. So this is case for it. And for such case, we can bound the error for the in terms of the epsilon. So let's see how we do it. So we just do the rescaling, and from the another reference, it is kind of top mathematics. So we can find the following real Fourier series, and that gives this equation. And remember that A and C, A are expressed in terms of cosine, and C and D are both functions, so we can get this one. Also, we can just define the sine delta as this and cosine delta as this because this holds. So if we define A theta as the following, we can get A0 like this. So it satisfies the condition of the lemma 3.5. So again, we can just do something. And then we can just bound the error of this approximation of like the A and C. So we just use the A1 as defined in here as a kind of intermediate. And then we can just bound this error very efficiently. So now we prove this one, the single ancilla quantum signal processing. this can be diagonalized. So remember, like W is kind of a summation of the e to the minus I lambda zeta something. So we can expect that this can be diagonalized in this basis. So we substitute V in here, and that gives something like this. So it just zeta becomes like psi plus zeta lambda plus minus. And then if we project this into the plus and G ancillary basis, it will give the calculation in this. And it again, it acts on the B. And now let's choose this large phi as pi over 2 and A to K equals 0, C to K minus 1, 0. It gives the cosine K theta, and then that's the Chebyshev polynomial. So we can approximate A lambda. Yes, this one. And the conditions, A lambda, clearly an even polynomial, and C lambda, odd polynomial, and A lambda equals 0, it is 1, and these conditions are satisfied, so we can prove this. So now this is the final step, the application to the Hamiltonian simulation. And we have the H, the encoded in the sentence form, and the theorem that we just proved allows us to use two Q queries to encode any function with the form AH plus ICH, where A and C is a bounded polynomials of opposite parity and degree Q. And if we can find some A lambda and C lambda that gives the good approximation of EI minus lambda T, then Hamiltonian simulation problem is solved. So there's expansion called the Jacobi and Garrett expansion. So we can approximate this one into this one, where JKT is a Bessel function of the first kind. And we identify cosine zeta as lambda. Then we can separate this into two terms. Note that there's a Chebyshev polynomial here. And we can like express like this one will go to be the A, and this one will be the part of C. But like, we cannot do the infinite summation, so we'll just truncate somewhere else, and the error due to truncation is known well. Yeah, for the mathematical details, please go here. Check this one, and this is where the Q term appears in the theorem. So Q can be like determined in terms of T plus log 1 over epsilon. So also note that the rapid converge by truncation arises as this is entire analytic. If it is not analytic, it will just, the infinite series will not converge well. So we can choose this one and this choice of these functions. It is only like epsilon close to satisfy conditions for the theorem. And remember the lemma that we proved just before, like that was the lemma for the case of like there's some epsilon errors, so we can bound these errors. So this is the proof of the theorem. And like how does it directly related? So for the case of the Hamiltonian simulation, we can combine the theorem one and the standard for encoding to like add T time evolution OT plus log 1 over epsilon for the Hamiltonian simulation case, and similar for the purified density matrix case. And note that there's some still ongoing research about the efficient simulations. So as long as I know, this is kind of a very efficient result, but there might be some recent results about it. So I found some papers. So and I'll test in the like this slide. So if you have further interest, please check this for the references. And also, there was some paper about named grand unification of quantum algorithms, and they try to explain the quantum algorithms in the term of the like standard form, and this gave some quite good results in the further some cases, because some say like this is possible because like this is kind of matrix problem, and we brought this into the larger space, so it kind of looks working well. So these are the references. Thank you for listening. And if you have any questions, please let me know. Yes, thank you.